Assalamualaikum and a very good morning. So today in this short video we would like to give a short summary of what we have recently learned in flight mechanic, which is about propeller and in place of the gas turbine engine turbofan. So this group, which is group 1, is consists of Sharul Malik, Anwar Mahmud, which is myself, Leon, and Nadiratul Akmal. So for propeller, before we go further into it, we need to know some of the terminology used. So some of the basic terminology used can be seen in this picture. So first is the axis of rotation, which is the axis in which the propeller will rotate around. The blade back, which is the part of the propeller facing in front of the aircraft. The blade face, which is the part of the propeller that was facing behind the aircraft. The blade angle or blade pitch, which is the angle in which the propeller is placed relative to the plane of rotation of the propeller, and also the chord. Since similar to a wing, a propeller also have its own chord, which is the distance between the leading edge and the trailing edge. So on the right side of this picture, we can see some more terminology. Basic, firstly, is the relative airflow or RAF. So the relative airflow is the airflow in which the propeller is operating on when it was spinning, and the angle of the relative airflow to the plane of rotation is known as the helix angle. So the angle of the blade angle, which is this, and the helix angle is the effective angle of attack. So the effective angle of attack, which is alpha in this picture, is basically the angle of attack which the propeller operates on. So next is the geometric pitch versus the effective pitch. So the geometric pitch basically means the distance of the propeller which the propeller travels in one revolution, which is indicated by this blue line. But since propeller suffers from inefficiency such as slip, the propeller effective pitch will usually be shorter than the propeller geometric pitch. So next is the difference between coarse pitch and fine pitch. So coarse pitch is the propeller position, the propeller blade pitch that is high relative to the plane of rotation, while the fine pitch refers to the low angle of blade pitch relative to the plane of rotation. So in this picture, we can see the difference between the high pitch and low pitch, in which this inboard propeller of this aircraft, which is an A400M, is on its high pitch, while the outboard propeller of this aircraft is in its feathered position, which is basically the maximum coarse pitch allowed by the propeller. So that's it for the basic terminology. We can continue on with the next part of this video.
Hi all, I'm Shahrul and now I would like to talk about the propeller efficiency. What is propeller efficiency? It can be translated as the ratio of thrust power delivered compared to the shaft power required to drive a propeller at given revolution per minute. Or we can simplify for better understanding as the propeller power produced divided by engine power applied. It can be expressed as the formula given in the slide, which is the propeller efficiency is equal to thrust power divided by engine power, or thrust horsepower divided by brake horsepower, or thrust time velocity divided by shaft torque times revolution per minute. This is the common formula being used to find the propeller efficiency or other components such as thrust or velocity. We can convert the horsepower into power, which is 1 horsepower is equals to 745.5 watts, and power can be derived from power work done divided by time. Hence, we can get power is equals to thrust time through speed or velocity. For efficiency of type of propeller, we know that propeller consists of fixed propeller and constant speed propeller. For fixed propeller, the climb propeller has low pitch angle which create less drag and result to the high RPM. It is suitable to be used for takeoff and climb, while cruise propeller has high pitch angle that create more drag and result to low RPM which is suitable for cruising. Compared to the constant speed propeller, we know that blade pitch can be changed in constant speed propeller. With that, we can see the variety of efficiency according to the pitch. For example, at high speed, coarse pitch is the most efficient, but at slightly low speed, the fine pitch is the most efficient to be operated. Propeller efficiency versus speed, we can see that when the through speed become faster, the efficiency also being decreased. The velocity, this is because of the velocity of air around the tip blade can turn into the shock wave, hence the efficiency depleted and thrust loss will be occur. For propeller efficiency versus angle of attack, when angle of attack is low at optimum speed, the propeller efficiency is also low because thrust produced is not sufficient compared to the engine power delivered. But if angle of attack is high at the optimum speed, the blade will experience thrust losses, hence efficiency will depleted too. With that, we know that there will be a suitable angle of attack to work with the optimal speed required so that we can get the optimal propeller efficiency.
Hi, my name is Lloyd, and as for today, I'm gonna talk about the thrust calculation for the summary of the propeller lesson. And then basically, there's two methods to find the propeller thrust, and for the first method is the derivation of momentum. So basically, when an engine rotates the propeller disc, it will produce a forward force, and the forward force also can known as thrust. And when thrust is equal to d over dt, bracket mv, which also known as the change in the momentum with time. When we derive it, we are able to get this equation, and when we separate it, we are able to get this equation, which is T equal to ME VE over delta T minus MI VI over delta T. And we know that when mass over T, we can know that it is mass flow. So we substitute it into the equation, we are able to get this equation, which is T equal to ME dot VE minus MI dot VI. So when we factorize it, we are able to get this equation. So for the second method, using the pressure difference, we know that F equal to P times A. And A is the area of the propeller, and P is the total pressure. And we can know that the total pressure consists of static pressure and dynamic pressure. When this is the equation that been substituted by the static and dynamic pressure for exit and for the inlet. And when we expand it, we're able to get this equation. And we know that static pressure for exit and for the static pressure for inlet are the same. And also for the formula for the dynamic pressure are 1 over 2 rho v squared. And we know that static pressure for both exit and inlet are the same, so we are able to cut off for both static pressure, inlet and exit. So we substitute in the dynamic pressure into the formula equation, able to get this equation, and when we factorize it, we're able to get this equation. And for the density is the density on the flying altitude. And for the first equation from the derivation of momentum, which is this, and for the second equation using the pressure difference are this, and when we expand it, we're able to get this equation. And for both equations, we are able to summarize the formula of mass flow, which we are able to get this equation. And for the density altitude, which must be remembered for this equation, and for the density ISA, and also for the temperature for ISA level, which must be remembered.
Okay, I, narrator, will explain to you about some interesting additional facts about propeller. For your information, propeller has varying pitch. As you can see on the screen right now, this is one of the example of a variable pitch propeller. Variable pitch propeller is functioned to maintain an optimum angle of attack by balancing the centripetal twisting moment on the blades and a set of counterweights against a spring and the aerodynamic forces on the blade. Next, we also have feathering propeller. Feathering propeller is when the blades can be rotated parallel to the airflow to stop rotation of the propeller and reduce the drag when the engine fails or is deliberately shut down. As for constant speed propeller, it is automatically adjusts the blade pitch according to the engine speed, thereby maintaining a constant engine speed for any given manual control setting. And lastly, for reverse pitch propeller, it helps to slow down the aircraft after landing and is particularly advantageous when landing on a wet runway, as wheel braking suffers reduced effectiveness. I will explain a little detail on feathering propeller. Okay, from the figure, there are three types of pitch for the propeller, which is first, fine pitch, which is often used when the aircraft requires low speed, especially during takeoff. And the high pitch is used for high speed. And lastly, feathered propeller is often applied when there is power failure. So basically, feathering propeller is the point at which the blades of the propeller are rotated to directly parallel to the airflow as shown in the diagram. As a conclusion, the purpose of feathering propeller is to greatly reduce drag and increase gliding distance. Furthermore, we also have windmilling propeller. Windmilling propeller is a typical process to start a jet engine in case it stops working mid-air. When the aircraft is cruising and the engine suddenly stops working, the method is used to start the engine. The cruising aircraft will experience air flowing strongly into the engine, thus preventing the turbine and compressor to stop rotating, and it will remain in motion. The pilot will then close the engine bleed air valve so that the engine could use the incoming air to start the engine and cause it to be reignited. Aircraft also have a constant speed windmill. The wooden propeller is one that pushes the aircraft forward, while this metal propeller has a very different function. It is called a constant speed windmill and is actually forced to rotate by the wash from the wooden propeller. As it spins around, you may see a thing attached at the back of this windmill. That is a generator which produces electricity for all the instruments in the aircraft. It is called constant speed windmill because as the air rushing past that varies gets faster or slower. The pitch of the angle varies, making sure the windmill keep rotating at the same speed to ensure the electricity produced remains at the same voltage. And that is for the additional information on propeller.
Hi all, I'm Shahrul and today I would like to talk about the working principle for turbofan. But before I'm moving on, I would like to introduce to you two types of turbofan, which is first the mixed nozzle and second unmixed nozzle. Now I would like to explain more about unmixed nozzle because a lot of aircraft nowadays is using this type of nozzle, and we can see that the core flow is not mixed with the secondary nozzle. The working principle of turbofan is consists of four main operations for better understanding, which is suck, squeeze, burn, and blow. There are two TS diagram on the slide, which is ideal cycle and non-ideal cycle. Non-ideal cycle happens because there will be losses along the operation and also the isentropic will not occur. For suck operation, the inlet of the engine make the relative airflows become slower to enter the engine, hence the pressure will be slightly increased. With that, the temperature also increase. The airflow be channeled into two parts, which is first bypass duct and second to the engine core. The amount of airflow entering the bypass and engine core can be expressed by using bypass ratio. Next is squeeze. Squeeze is where the air being compressed by the compressor. There are several stages in the compressor which it is becoming smaller and the pressure will be increased to channel enough energy for the air before entering the combustor. And next is burn. Burn is where the air being mixed with sprayed fuel combustion. Here, it is important so that the energy that be released from the combustor is high enough to rotate the turbine, because as we know, for turbofan, there are two spools or more because the turbine being connected to several parts in the engine with different shaft. For example, from turbine to compressor and from turbine to fan. Next is blow. Blow is an important process to let the air be expelled out of the engine. For this type of turbofan, there are two types of nozzle, which is first the core engine from the primary nozzle and second from the bypass duct, which is the secondary nozzle as I mentioned. So here we can see that the third law of Newton take place because the air being forced out at the back of the engine, but the aircraft is moving forward. Hence, it shows that there are consequences for the forces at the opposite direction. Here, we can also detect the ratio of bypass, whether it is high or low. High bypass means a lot of air being channeled into the bypass duct compared to the core engine. Next is the advantage of bypass. First, it is to create additional thrust for the engine. Second, It also makes engine quieter by blanketing the exhaust air exiting the engine. And last but not least is to make the engine cooler.
So now we look into an example of a turbofan engine. One of a good example of a turbofan engine is the Pratt & Whitney F135 engine, which is currently used on the F-35 Lightning II jet fighter, the newest jet fighter produced by the United States. This engine is developed from the old Pratt & Whitney F119 engine, which is used by the F-22 Raptor, another modern fighter produced by the United States. For the specification, the engine is a two-spool axial flow augmented turbofan, which means it have an afterburner with a full length of 559 cm and a max diameter of 117 cm. It have a dry weight of 1,701 kg. Dry weight here means that the weight without the fuel and the oil on the engine. It is made up of a 3-stage fan and a 6-stage high-pressure compressor for its compressor system, an annular combustor for its combustion system, a 1-stage high-pressure turbine and a 2-stage low-pressure turbine for its turbine system, and a bypass ratio of 0.57 to 1. For its performance, it can produce 128 kilonewton of maximum military thrust. Military thrust here means maximum thrust without the afterburner, and 191 kilonewton of max thrust with its afterburner on. It have an overall pressure ratio of 28 to 1 and a turbine inlet temperature of 1980 degrees Celsius or 2260 Kelvin. It have a thrust-to-weight ratio of 7.47 to 1 when operating on its military thrust, or 11.47 to 1 when operating with its afterburner. The engine did not stop there, since future development is planned for the engine and also the aircraft itself. One of the applications that is planned for the engine is the usage of the adaptive cycle engine. Adaptive cycle here means that the bypass ratio can be changed by the pilot based on what they need at the time, such as if the pilot requires the engine to perform at its maximum thrust, such as during combat or aerobatic flight, the bypass ratio can be set to low, where more air flow through the core instead of the bypass. In this mode, the engine will operate at its higher thrust, but at the expense of its efficiency. But if the pilot requires the engine to operate more efficiently, the bypass ratio can be set to high, which means a greater ratio of the air flow goes through the bypass. This means that the engine will produce less thrust, but perform at a greater efficiency. So I think that's all for the example of the engine. We can continue on with the next part of the video.
Hi, my name is Lud. So today I'm going to talk about the turbofan thrust calculation. As we can see from this diagram, we can know that the turbofan engine will produce two types of thrust. For the first thrust being produced is by the fan, and for the second thrust produced by the core of the engine. Before we proceed to the next step, we must know the term used in the thrust calculation. As for the mass flow, we can know that the mass flow initial of the inlet in the turbofan engine are equal to the mass flow of the fan plus with the mass flow of the core of the engine. As for the bypass ratio, we can know that bypass ratio of the turbofan engine is the ratio between the mass flow rate of the bypass stream to the flow rate entering to the core of the engine. And this is the equation then been substituted by the derivation of momentum for each part of the engine, which for the part of the fan and also part of the core. And when we expand it, we are able to get this equation. And when we factorize the equation for the same term, we are able to get this equation. As we can see that mass flow fan plus mass flow core are similar to the mass flow for the inlet of the engine. So we substitute it into the equation and we are able to get this equation. And how we get this equation, this part, by rearrange the bypass ratio formula. So we arrange it and we are able to get this equation. We substitute it and we are able to get this equation.
For For the example of efficiency calculation, we will be using the JT9 engine which have the information as follows. From the previous calculation, these are the informations obtained. In order to achieve the propulsive efficiency, we can use this formula. As we know, the JT9D turbofan engine has two parts, which is the hot and cold part. So we will obtain two values of propulsive efficiency, which the first one is the 1.6% and the second one is 3.6%. Next, we will continue with the thermal efficiency. By substituting the formula, we will obtain a 26% of the thermal efficiency. As for the overall efficiency, we know that it is the product of the thermal efficiency and the propulsive efficiency, which has the value of 9.36 times 10 to the power of negative 3. And that is all from our group. Thank you.